Okay, so we've been talking about convergence of infinite series, and we looked at a few tests for this, right? We can test the Cauchy criterion, where we add a whole bunch of terms together and make sure they stay small. We had comparison tests, where we say we can take the terms in our series and compare it to maybe a simpler series that it's easy to see whether it converges or diverges. And then we did the integral test, where we said maybe these kind of terms, we don't really know how to add them up, but maybe we know how to integrate them and decide if the integral converges. So there's some good tests. They're not always easy to apply. It depends on your series. One of the disadvantages is they sort of require information really about very global behavior of the series, right? If you're doing the Cauchy test, you need to add up a whole bunch of terms and make sure that stays under control. If you're doing a comparison test, you need to somehow be able to conjure up a series that's easier to work with and that you can easily compare terms. Integral test, well, you've got to be able to integrate this thing and decide if the integral converges. What would be nice a lot of the time is if we don't need this kind of global behavior, if we kind of just look at one term or just two terms, neighboring terms, and somehow look at them, and that's enough to decide what's going on. So this is sort of another goal. Sometimes, this pen looks like it's on its way out. Sometimes it would be nice to have it would be easier to try to study convergence of series, infinite series, using only information that's kind of local, not having to look at a whole bunch of terms and how they behave. So about terms in the series. Okay, I mean, we tried this right back when we were first thinking about convergence of sequences and series. We tried this with the harmonic series, and our first attempt at doing really local behavior didn't quite work. So if we come back to the harmonic series, okay, where here we have our general term an is equal to 1 over n. And we add them up. Okay, we know that the terms are getting smaller. Right? This is certainly less than an. The terms are getting smaller, and we also know that that's not sufficient to prove convergence. And of course, this, if we add the terms up, it doesn't converge. Okay, so this was not enough for convergence. And the idea here, the reason, in some sense, this is not enough for convergence is that even though these terms are getting smaller, in the limit somehow they're kind of the same size. All right, so if we were to look, for example, at an plus 1 divided by an, right, 1 over n plus 1 over 1 over n. What does that do in the limit as we take n to infinity? It goes to 1. So this goes to 1 as n goes to infinity. Right? In other words, if we sort of say an plus 1 over an is basically equal to 1, it's very close, that means that an plus 1 is really kind of approximately equal to an in the limit. Right, so the terms are getting smaller. They're not getting smaller very quickly. In the limit, these terms are the same size effectively. But this is an idea, at least for another test. What if we have terms that, if we compare them locally, they're not the same size in the limit? Maybe in the limit, an plus 1 actually is significantly smaller than an. Maybe that would be good enough. Maybe if we look at this kind of limit and it's less than 1, then we can say not only are the terms getting smaller, they're getting smaller relatively quickly, and maybe it's quickly enough for us to have some hope of convergence. And something like this is potentially a lot easier to look at than having to add up a whole bunch of terms or use some kind of global test or be able to do a complicated integral. So this is basically your ratio test. I'm going to write it a little bit differently than you've probably seen it in calculus. Okay, so this is our ratio test, and then we'll see why it works. But this is the motivation. The terms are getting smaller, and they're getting smaller fairly quickly. So we're going to assume that we have a series, an, and all the terms are positive. Okay, so all the an are positive. Now there's two parts to this test. One is to try to decide if the series converges. One is to try to decide if it diverges. And there's some middle ground where the test doesn't really tell us anything. So what we're going to look at is, I'll leave a gap here. So we're going to look at an plus 1 over an. What we're not going to do is assume that this limit actually exists, right? So when we look at these ratios, a2 over a1, a3 over a2, a4 over a3, there's no reason in general why this limit has to exist. The terms could bounce around. So what should exist if these things are behaving themselves, right? If these things are getting smaller, what we should at least have is a limit superior. So we're going to look at the limit superior. Okay, and we're going to say that, all right, these ratios are bouncing around, but as long as in the limit they don't bounce too high, they stay definitely well below 1, then we should be in business. So if this limit superior is not 1, but strictly less than 1, then we're going to say that these terms are getting smaller, and they're getting smaller quickly enough, and the series is going to actually converge. So then we're going to say an converges. Okay, then we're going to similarly try to have a test for divergence, right? We can reasonably expect if these terms are getting bigger in the limit, an plus 1 is getting bigger than an in some sense. That's not good for convergence, right? We don't have much hope then. But again, these things could bounce around a little bit. So some of them might be bigger than 1, some of them might be less than 1. As long as all of them are bigger than 1, all of these ratios are sort of bigger than 1 in the limit, we know we're in trouble and we don't have any hope of convergence. So here we need to look at the limit inferior. And if the smallest these ratios ever get is still bigger than 1, then we're in trouble. Then our series is going to diverge. Okay, so this is our ratio test, and then there's middle ground, right? We could have a case where neither of these two conditions is met, and then we just don't know. The ratio test doesn't necessarily tell us anything. But again, the good news is this is very local behavior. In some settings, at least, it's going to be a lot easier to work with than some of our other tests. Okay, so let's prove at least part of it. The other part of the proof is not going to be so different. OK, so we're going to start by assuming this is true. We have this limit superior, and it's less than 1. OK, so let's define L to be the limit superior of this thing. And we are just going to suppose it's less than 1. All right, we're working with the limit superior here as an important component in the statement of the theorem. So I'm assuming that I might have to write down something about what the limit superior means, right? That's what we always do in these proofs. We write down the thing that we know. And the thing that we know is that this limit superior is less than 1. If I'm going to write down the definition of the limit superior, usually I need an epsilon. So I'm going to try to come up with an epsilon. So let me motivate this a little bit. So we've got our number line, and here's 0, and here's 1, and L is somewhere. And we know there's a definite gap between L and 1, right? L is strictly less than 1. So what I'm going to do is I'm going to pick my epsilon to be anything that's smaller than this gap. In other words, I'm going to pick a number between L and 1. I'm going to call this R. Epsilon is going to be this gap. Okay, so if we write this precisely, let's choose some R such that it lies between L and 1. And we define epsilon to equal R minus L. And this is a positive number. We need a positive epsilon. Okay, and then we say, all right, we know something about this L, right? L is the limit superior of this thing. So let's write down a little bit about what that tells us. So from the definition of the limit superior, okay, we know. So we know that L is acting like an upper bound in the limit, right? So we've picked our tolerance epsilon, and as long as n is big enough, these terms, these ratios, can't get bigger than L plus epsilon. So we know there exists some n star such that if n is bigger than n star, then an plus 1 over an, right? L is trying to act like an upper bound in the limit. It's not actually an upper bound, so we have this little plus epsilon tolerance that we allow. You believe this? Okay. If you don't believe it, speak now, because I don't want to lose you now. And there's another name for L plus epsilon. We had a shorter name for it. If we go look over here, right, L plus epsilon was R. And this was a number that we know to be less than 1. Okay, so let's rearrange this a little bit. This means that an plus 1 is less than an times R. Right, and this is always true as long as n is big enough, for all n bigger than n star. That means an plus 2 is less than an plus 1 times R. But an plus 1 is less than an times R. So this is less than an R squared. All right, and we can keep playing this game with the terms. An plus 3 is going to be less than an R cubed. And in general, an plus k is going to be less than an times R to the k. Okay, and now things are starting to look good for us. Because now if I start adding up all of these terms, an plus 1 plus an plus 2, an plus 3, as far as I want, each of those terms I can compare to something that looks like this, right? And this is a fixed n, And it's the k's we're adding up over. So we're adding up, r plus r squared plus r cubed, so on, where r happens to be a number less than 1. Should suggest to you another test that we can use. Right? Which test am I going to use? I'm about to use a comparison test where I'm comparing to a geometric series. Okay? So we know that this sum, so k equals 1 to infinity of an r to k converges. Right? It's a geometric series with r less than 1 in magnitude even. And that means our comparison test tells us that if I add up terms that look like this, that will also have to converge, because these are positive terms. We started by assuming these are positive terms. So by the comparison test, this is going to imply that k equals 1 to infinity of a n plus k converges. This is almost my original series. All that's happened is instead of starting at a1, I've started somewhere along the line at an plus 1, right? So I've missed the first few terms. I've missed the first n terms, but n is finite, right? So this series converges. Now I'm going to add on additionally a1 plus a2 up to an, but those are all just finite numbers. We're adding on finitely many of them. That's not going to break convergence, right? And we've talked about this before when we're looking at convergence of series or convergence of sequences. It doesn't matter what a1 does. It doesn't matter what a2 does, right? As long as eventually these things get into line and behave themselves, we're in business. Okay? We've found a point, right? Once we had n star here, these terms fall into line. They behave themselves. We can add them all up. They converge, no problem. That means the first few terms before n star are not going to break that. So that means that indeed this original term, this original series, also converges. And that is what we wanted to show. Any questions on the proof? All right, so again, it comes back to using our earlier tests. We're not reinventing the wheel. We're using the comparison test. We're using the comparison test cleverly once in this proof, and now we don't have to do it every time we see a new series. Now every time we see a new series, if it looks like it would be easier to compare this ratio, we can just do that and not have to run through all of this argument every time. Okay? The proof of part B is similar, and it should be in the book. Right there, you'll write down what it means for something to be a limit inferior, and you use a comparison test for divergence this time. Okay, so for example, say I have this series, n over 2 to the n. Okay, I mean, this doesn't look like something where I really want to use the integral test, for example. That looks hard. It's not that obvious what kind of a comparison test you would do here. But maybe we can do the ratio test. So we know that these terms are all indeed positive. So we know we should look at the ratios. So if we look at an plus 1 over an, what do I get? I get n plus 1 over 2 to the n plus 1. And then over an is 2 to the n over n. That's 1/2 n plus 1 over n. Okay, and then if we're going to use the ratio test, we need to either look at the limit superior or limit inferior of this. In this case, they're both the same. This thing has an actual limit, right? And we know when there's an actual limit, it's going to agree with our tightest upper and lower bounds in the limit. So here we're going to say that the limit superior of this thing is equal to 1/2, which is certainly less than 1. Therefore, the series converges. Okay. Again, this kind of example you should have done before. Now, there are other examples where this limit doesn't exist. We have to really look at the limit superior or the limit inferior or both to make a decision. Okay, so for example, let me take this series where our ANs can have different forms. 1 over 2 to the n if n is odd, and 1 over 3 to the n if n is even. Okay, so this is like 1/2 plus 1/3 squared plus 1/2 cubed plus 1/3 to the 4th, and so on. Okay, if we want to try our ratio test, now these terms are all positive, so that's fine. If we want to try our ratio test, we need to look at an plus 1 over an, but there's two different things that could happen depending on whether n is even or odd. So if n is odd, then an plus 1 over an, we should do this carefully. Yep.
So both odd and even have to converge.
Right, so when we do this ratio, the limit superior of this has to be less than 1.
Right.
So that means we have to look at what happens when n is odd. We have to look at what happens with n is even. Whichever of those does the biggest thing in the limit, that's the one we have to look at and have to keep less than 1. Okay, so here, n is odd. That means n plus 1 is even. So an plus 1 is going to live in this category here. 1 over 3 to the n plus 1. And an is odd, so we have 1 over 2 to the n. Okay, so if I simplify this a little bit, I have an extra 3 here. I'm going to pull that out in front. And then a 2 and a 3 that are both being raised to the nth power. And what's that? So when n is odd, this ratio gives us, that looks like a 2 over 3 to the n. Yeah. Okay, we have to also do this when n is even. Okay, so when n is even, n plus 1 is odd. So we're going to be up in this category here. 1 over 2 to the n plus 1 divided by 1 over 3 to the n. Okay, so again, we get an extra 2 this time, and then a 3 over 2 to the n. Okay, and now if we're going to try to use the ratio test, we should look at the limit superior or the limit inferior or both of these things. So what's the limit superior of this whole thing? That's right. So if the limit superior means what we're really happening with these ratios is they're bouncing around between something that looks like 2/3 to the n, which gets small, and something that looks like 3/2 to the n, which gets big, right? So if we're looking for the upper bound in the limit, it's always going to keep bouncing back up to this 3/2 to the n, and that's going to go to infinity. So this is actually infinite.
We're looking at the limit inferior.
So the limit superior test told us nothing. We should look at the limit inferior. What's the limit inferior? The limit inferior is 0. Exactly. So again, we're bouncing between something that looks like 2/3 to the n, which is going to go to 0, and something that looks like 3/2 to the n, which is blowing up. Limit inferior, we care about the lower bound. And this lower bound here is going to 0 on us. So what does that tell us from the ratio test? It tells us nothing, exactly. So in this case, the ratio, okay, you can manufacture examples like this. There are plenty of examples like this where the ratio test would actually tell you something. But it won't always tell you something, right? So in this case, ratio test is a big question mark. And it's a big question mark because this is not less than 1, and this is not bigger than 1. OK, so the ratio test is great. It does help a lot. It helped with this example. It helps with lots of other examples. It doesn't help with everything. But we shouldn't give up yet. We saw when we built this test, we were really trying to compare to a geometric series, right? The whole goal of building that test was we looked at an plus 1 over an, and we said we'd like to show that in some sense an plus 1 gets smaller than an fast enough. There's other ways to compare to a geometric series. So maybe if we do the comparison in a more clever way, we can get something. So there are other options for comparing two familiar series such as the geometric series. Yes?
For this example,
Yeah.
since the series can be written as the sum of two convergent series, would that be enough to show?
OK, I was waiting for somebody to ask that. Because we know this can be written as the sum of two convergent series, is that good enough? The answer is you have to be extraordinarily careful when you're doing that. If we have time at the end of class, I'll do an example like that. What you want to do is say, what you're trying to do is say, let's take this series of terms and sort of group them, rearrange them, pull out all the ones that look like half to the n, pull out all the ones that look like a third to the n. You can do that sometimes. Sometimes you can get into an extraordinary amount of trouble. It turns out by taking terms in a series, an infinite series, and rearranging them, even if you start with a convergent series, if you rearrange them, you can sometimes make the series add up to a different value. In fact, you can make it up, in some cases, add up to any value that you like. So it turns out that won't be the case for this series, but for some series it is. You can take a convergent series and say, I'd like to make this add up to pi plus 3. There's a way of rearranging it to make it add up to pi plus 3. So you have to be really, really, really careful when you want to change the order of infinite series. If we have time, I'll say more about it, and if not, I think the book does talk about this a little bit. OK, so we didn't learn anything here. What we know about geometric series is it looks at terms that look like r to the n, right? And this converges if r is less than 1. R is really the nth root of an. So this is something that actually, it's sort of even more local than the ratio test. The ratio test said we need to compare two neighboring terms. This sort of test actually just looks at individual terms, and it doesn't matter how they compare to each other. And what broke us here was comparing these terms, and depending on the order they got compared in, either the 2 could go on top or the 3 could go on top, and those give us very different results. Here, maybe it doesn't matter so much. This you should recognize as looking like your root test, right? And this already motivates, why does the root test make sense? Because it's really trying to compare to, again, a geometric series and saying, geometric series has this property, maybe other series have this property. So this is our root test. Okay, so if, again, we have positive terms, okay, and we define alpha to be the limit superior of these things. Again, these values can bounce around. We're not going to assume that the limit exists. And there's 2 parts to this. If alpha is less than 1, okay, then the series converges. And if alpha is bigger than 1, then it diverges. Okay, so let's try to prove it. We have intuition already. Right? The intuition comes from saying this is how the geometric series behaves. So let's see what we can do here. So in part A, I have alpha less than 1. I'm going to pick my epsilon, right? We know we're playing with the definition of the limit superior. We should have an epsilon. I'm going to pick it exactly the same way I did before. Okay, so let's choose some r that lives between alpha and 1. And let epsilon equal the difference between r and alpha. Okay, same as the last time. Okay, actually this proof, at least the proof of part A goes the same as last time, basically. So again, we know there exists some n star such that if n is bigger than n star, right, then how do we define the limit superior? We're taking the limit superior of an to the 1 over n. So an to the 1 over n should be less than alpha plus epsilon, which again is r. Okay, and then we're doing exactly what I did here when I motivated the test. Just say the nth root of this is less than r. Then if I take things to the nth power again, this is going to be less than r to the n. Okay, and we're in business to do a comparison test again, right? This guy, r is less than 1, this guy converges. So this guy's going to converge when we add them up. So again, by the comparison test, we get that an converges. Okay, part B is a little bit different than with the ratio test, right? With the ratio test, we needed to look at either the limit superior or the limit inferior. With the root test, it's actually always the limit superior, even if we're testing for divergence. So this part of the proof is going to be a little bit different than the other one. Okay, so part B. This time we have alpha bigger than 1. Okay, again, I should have an epsilon. I need a different epsilon this time because that epsilon assumed that alpha was less than 1. This time I'm going to, again, I need a positive epsilon. So I'm just going to use the fact that alpha is bigger than 1. 1 minus alpha is a positive number. So let's let epsilon equal alpha minus 1, which is positive. All right, we used one property of the limit superior here, that all of the n's, all of the terms, once we got big enough, stayed below this bound. Now we want to use the other part of the limit superior definition that says, but this is actually a tight bound in the limit, right? So that no matter how far along we go, we're going to keep jumping up close to this again, right? Up bigger than L minus epsilon, no matter how far we go. So that what that says is there exists infinitely many values of n. Right? No matter how far along we go, we can always find another value of n that's going to jump up such that an to the 1 over n, okay, is bigger than L minus epsilon, alpha minus epsilon. Right? That was part 2 of the definition of the limit superior. It said, find me a value that's bigger than alpha minus epsilon. You can do it. And I say, well, let's restart here. Find me another value that's bigger. You can always do it. It always jumps back up and tries to get close to this alpha again. And this was equal to 1. What does that mean? That means that an itself is also bigger than 1. Okay, for infinitely many values of n. All right, now we're adding up these an's, right? We're adding them all up. And infinitely many times we're adding on a term that's bigger than 1. That's a problem, right? That means we can't converge. Another way of saying this is certainly not the case that these terms are going to 0, right? We know if a series converges, the terms have to go to 0, right? Otherwise, we're doing what we're doing here, is we keep adding on big numbers. And that means it cannot possibly be the case that this converges. Okay, so this is our root test, right? It's in some sense not that different from the ratio test. We're still doing a comparison with exactly the same series as before. We're just setting up the comparison in a different way. And the different way gives us a different test, yes?
So if in other tests, the fact that it doesn't converge does not mean it diverges. What makes it different here?
So divergence means not converging, right? So some of the tests just give sort of a no-call result. Some of the tests come back and just say, I don't know, right? That's what happened when we just did the ratio test before. It didn't say that failure to converge. It just said, I'm not sure, right? But as soon as we have a result that says no convergence is how we define divergence. So we can come back to our earlier example and see if we can get a little farther with that. Okay, so again, we're adding up all of these ANs, where AN is either 1 over 2 to the n or 1 over 3 to the n. Okay, all of these terms are positive. We need that for the root test. We know we're going to need to take the nth root of these things. Right. That still gives us an even-odd distinction. It's going to be a half if n is odd, and a third if n is even. And if we want to use the root test, we know that we have to take the limit superior of this. So what is the limit superior of these terms? 1/2, exactly, right? So again, these values bounce. They don't converge to any limit, they bounce. But the biggest they bounce to is a half. So here our limit superior is going to be a half. And we look at that and say, that's less than 1. We're in business. So right away we can say this series converges by the root test. Yes?
When we were doing sequences, we had this notion that if you took an infinite subsequence of a divergent sequence, it diverged still? Or something to that effect?
If you took an infinite subsequence of a divergence sequence. Oh.
Or maybe it was actually, I guess that doesn't actually follow. I guess infinite subsequence of a convergent sequence. Also.
Right. So if you have a convergent sequence, then you can take any subsequence that will also converge to the same limit.
Right.
Absolutely.
If you take a subsequence of the terms of a series,
Yes.
does that kind of logic still follow? Or no?
So if you have a series that converges and you take finitely many of them, yeah, so then you could do a sort of comparison test, for example, or working with the partial sums, for example. If you've left out some of the terms, you can sort of bound your partial sums in terms of other partial sums that are also bounded. So yeah, you could get there. A lot of this, all of these are really just clever ways of doing comparisons with simpler things, right? All of these tests, the ratio test, the root test, those are fancy versions of the comparison test. They're just sort of fancy versions where we've said, here's a pattern, a way we can set up the comparison test. It takes a bit of work. And once we've done that once, we can apply it for lots of different things. OK, these were all series where we assume the terms are positive. Of course, the series won't always have positive terms. So there's a couple things you can do. One is one thing that we did with integrals is we said sometimes, okay, this thing maybe changes sign, but maybe if we just take the absolute value, it still converges absolutely, and that'd be good enough. So we can certainly do that here. A series AN converges absolutely. Okay, if when we add up the absolute value of the terms, we get convergence. Okay, and just like with the integral test, or with improper integrals, right? If you have absolute convergence, you automatically get convergence of your original series. So that's a theorem. If a series converges absolutely, then it converges. All right, that's a 1 or 2 line proof where you just check the Cauchy criterion. And you can bound things in terms of their absolute values, just like we've done lots of times. OK, the converse doesn't hold, right? Just like for integrals, the converse doesn't hold. So absolute convergence implies convergence. Convergence doesn't imply absolute convergence. So there's another category. We'll say that a series converges conditionally. Okay, if it converges, okay, but does not converge absolutely. Okay, so we have lots of tests that we can use to check for absolute convergence, right? So if you happen to have a series that has sign flips in it, but the sign flips don't really affect whether or not you get convergence, then you can just use any of our old tests, right? So for example, if you do something like this, minus 1 to the n over n squared, this is going to converge absolutely, right? If you get rid of the minus 1 part, you get convergence. You can do an integral test. You call it a p-series, whatever you want to do. So this converges absolutely. Okay, integral test, whatever. Okay, so you know it converges. If instead of an n squared here, I just had an n, well, now all of a sudden we can't make that argument, right? And we know that our harmonic series diverges, right? So if I write that down, so if we have our alternating harmonic series, we know this doesn't converge absolutely. But that doesn't tell us whether it converges, right? Okay, we have terms. We add them up. If they're all positive, they grow. But now with the minus, there's the potential for cancellation. They might grow. They might not. We're not sure. And right now, none of our other tests are going to tell us how to deal with this, because all of our other tests start by assuming all the terms are positive. And we know if we make the terms positive, then we're toast. Okay? Our current tests, our existing tests, will fail here. So they fail to give us any information, one way or the other. Okay, so if we want to look at sort of real life things where terms can bounce between positive and negative, we need a test that is going to allow for that. Right? And this is your alternating series test. Okay, there's 3 criteria that we're going to have to check for this. So let's let an be a decreasing sequence. It's one thing to test. Okay, of positive numbers. Okay, that go to 0. Okay, so 3 things to test. We look at the terms without the -1 part in front of them, and we say, okay, these terms are all positive. Then we're going to multiply them by a -1 to the n. These terms are positive. They're going down, right? They're not allowed to bounce, right? They go to 0, and they go there monotonically. Then we can say something about convergence. Okay, so then -1 to the n or n plus 1, doesn't matter, converges. Right? And again, it doesn't matter if this is -1 to the n or to the n plus 1. You get the same behavior. Yes?
Could you also have that less than half the values are negative as long as an infinite value, a number of them are negative?
That less than half the values are negative.
Like, because you could do -1 to the n, -1 to the n plus 1. What if you did something a little more arbitrary that said if n is divisible by 4, it's negative?
So you may be able to do something like that. You'd have to work out the test.
Okay.
Again, this is where you have to be really careful. These kind of theories are the really dangerous ones, where you start trying to rearrange terms, you get into trouble. But I'm going to show you the proof for this, and you can certainly imagine reworking this proof for your own case. Now, I'm not using any of our old tests. I'm not using comparison tests, things like that, because they are just not valid here. Right? So we're going back to definitions, Cauchy criteria here, because that's what we have that currently works in general. Okay, so I just said it. We're going back to the Cauchy criterion because that's all we have that works here. That means we need to look at partial sums. So our goal is going to be to show that, okay, the sequence of partial sums convergence. Okay, we're going to do it in the nice case where, again, we have alternating positive, negative, but you could certainly imagine reworking this argument for a different pattern of plus and minus. You might have slightly different conditions, though, on, for example, how quickly they're decreasing. I imagine if you wanted to do something like that, positive, negative, negative, positive, negative, negative, you would have to be a little more precise about how quickly things are decreasing. OK, so I'm going to do a bit of an even-odd split here again, because it's sort of convenient, right? As long as I have an even number of terms, I can go positive, negative, positive, negative, positive, negative. And that's why I put the n plus 1 here, just so the first term would be positive. It's not a big deal. Just is going to make it a little cleaner. So let's start with the even partial sums. We've got to do them all, but we're going to start with the even ones. So S sub 2k. So I'm doing a partial sum where I'm adding up the first however many terms, but I'm just going to stick with the setting where the number of terms I'm adding up is an even number. Again, we've got to deal with the odd ones later, and we will. But let's start with this. This is A1 minus A2, A3 minus A4, plus A2k minus 1 minus A2k. And I'm going to start by trying to show that these, as long as I stick with even, ending at an even point, I can control this sequence. So if I look at the subsequence, S2, S4, S6, S8, this subsequence, I'm going to show that we can keep that one under control first of all. OK, so I have this. On the other hand, I have S2k plus 1. That's the next term in these even partial sums. Right? It's the same kind of deal. a2k plus a2k plus 1 minus a2k plus 2. All right, which one of these numbers is bigger? You think the upper one is bigger? You think S2k plus 1 is bigger? Well, let's look. So the easiest way to tell if something is bigger than the other is just to take the difference between them, right? And then the sign of this will decide which is bigger. So if we subtract these, we're going to mostly get cancellation except for these last two terms here. So we get a2k plus 1 minus a2k plus 2. Okay? We know that this is a decreasing sequence, right? That means this number is smaller than this number. So this is bigger than 0 since the a ends are decreasing. So indeed, the second one is bigger. Okay? So if we look at the sequence S2k, this is going to be an increasing sequence, right? If we replace k with k plus 1, the value gets bigger. Replace it with k plus 2, the value gets bigger again. So this is an increasing sequence. It's monotonic. What do we know about convergence of monotonic sequences? If we need to show it has an upper bound, exactly, right? So we already know this is a sequence that's going up. Those are easier to work with, sequences that go in only one direction. We just have to show it's bounded. If it's bounded, then it can't go to infinity. It's going to have to stop somewhere. So we need to show that it's bounded above. Yep. We haven't gotten to the whole series yet. Right now we're doing just partial sums. Right? So the partial sums is a sequence that involves adding up the first however many terms in this series. Okay, so it's increasing. Now let's see if we can find a bound. So if we look at S2k in general, this is, I'm just going to take this and rewrite it a little bit. So a1 minus a2 minus a3, right? Minus so on, minus a2k minus 2 minus a2k minus 1. So I've got my plus a2k minus 1 here. And then I still have to include this guy. What do we know about a2 minus a3?
Positive.
It's positive, right? So the terms are going down. So these are the A's. The A sequence is different than the S sequence. The A's are going down. So that means this difference here is certainly positive. All of these other differences are positive. And what do we know about this number here?
Smaller than negative.
Right. So we're subtracting off, again, this is a positive number, right? We assumed all these terms were positive. So what do I have here? I have a1 minus something positive, minus something positive, minus something positive. Right? Whatever I've got here is certainly bounded above by a1. Because all I'm doing from there is subtracting stuff off. A1 is just a number. right? I don't know what number it is, but it's some number. So S2k is bounded above. Okay, and we said monotonically increasing. So it converges, exactly. So we haven't done all the partial sums yet. We've only done the partial sums that include an even number of terms. So that's not everything. But at least we know that the limit as k goes to infinity of S2k is equal to S, which is some number. I don't know what it is, right? But we know it has a limit, which exists, and it's a finite number. So the even partial sums behave themselves. Now we have to worry about the odd partial sums. We need all the partial sums to be converging to the same limit. So for the odd sums, let's see what we can get. So now we need to also look at the limit as k goes to infinity of S 2k plus 1, the odd ones. And let's see what we can do with that. Well, that's equal to, we add up the first 2k terms, and then we have to add on the one term that got left out.
Isn't that just the same as the top limit?
And that's right. It's the same as the top limit plus whatever this goes to in the limit. What does this go to in the limit?
0.
This goes to 0. That was one of our assumptions, right? So we've actually used all our assumptions here, that these a's are positive, that they are decreasing. We needed in a couple places that they're decreasing. We used right here that it was positive. And now we're going to use the fact that it goes to 0. So this is actually just equal to s plus 0, which is s. So they both converge to the same thing. Right, so that means if I look at my general partial sums, okay, so for our general partial sums, take the limit as n goes to infinity of Sn. Okay, and as n is going to infinity, it's jumping between even and odd values. But it doesn't matter which of those values it's taking. These partial sums are trying to go to s in either case. So this is indeed s, which again is finite. Okay, so we started with our series, our alternating series. We've looked at the sequence of partial sums, and we said, great, the sequence of partial sums converges. That's how we defined convergence of an infinite series, right? When we first wrote down an infinite series and said, what does this mean for us to be able to add this up and have it make sense? We said, let's look at the partial sums. And if the partial sums converge, we'll say that the series converges. This is nothing but the definition. So we're going to say, indeed, our series, minus 1 to the n plus 1 an, converges. Okay, and this we just checked the definition. Any questions on that? Okay. Again, you could imagine modifying this for other types of problems. But you might have, an A2 minus A3 minus A4 or something. You'd need these to be getting small quickly enough that you could really verify that these groupings were positive.
I don't know if I'm remembering
Yep.
correctly.
So for a series to converge, the sequence of terms has to go to 0, yeah. But it's not enough to guarantee convergence, but it's definitely necessary for convergence. Okay, so if we go back to our alternating harmonic series, so we have our minus 1 to the n and 1 over n. If we look at an equals 1 over n, this is certainly positive. It's certainly decreasing. Okay, and these terms certainly go to 0. Okay, and now that's all we need to check, right? We could have gone and taken this series and tried to plug it back into definition to work out partial sums, right? And we would have gotten this kind of result. But because we did a very general result, we can use it for lots of different things now. This is enough to say that the series converges. Okay, by the alternating series test. Okay? So, and this is an example of a series that's going to converge conditionally, right? Because we know if we take the absolute value, it doesn't work. So this converges conditionally. Any questions on that example or on this test? All right, let's play a game with this series. I think I'm going to change this minus 1 to n to minus 1 n plus 1. But that won't affect our conclusions about convergence. Here, this is something like 1 minus a half plus a third minus a quarter, and so on. Okay, and we know this converges, right? We just showed it converged. Actually, it converges to the natural log of 2, it turns out. I'm going to convince you of that in one line. Remember that we've done Taylor series. If you do the Taylor series for the log function, okay, it's just a Taylor series. Okay, if I put in x equals 1, I get my alternating harmonic series. So log of 2, put in x equals 1. 1 to the n's are just all 1. Okay, now what I'm going to do is I'm going to rearrange the terms in this series. So we have a series, it converges. We add things up, partial sums stay under control, it's great. I'm going to now take the same terms and add them up, but I'm going to add them up in a different order. So let's rearrange the terms. Okay, and the pattern I'm going to use is I'm going to take 2 of the odd numbered terms, and then 1 of the even terms, and then 2 of the odd terms and 1 of the even terms. Okay, so I'm going to take 2 of the odd terms, 1 plus a third. Yes?
If it's different,
Yes.
which I'm assuming
It's going to be, yes.
would that violate, is it associativity or common of addition?
So remember, the rules we have for addition assume we're adding up finitely many things. We're not adding up finitely many things here. So your common sense breaks. It's not the math that's broken. It's simply your intuition that's broken.
Okay.
So I take two odd terms, and then I say, now I grab the first even term. Now I'll take the next two odd terms. And then I say, where's the next even term? And so on. But all the terms are going to make it into this series eventually, right? They're just being written in a different order. Okay, so let's see if we can line this up nicely. So ln of 2 is what we started with. 1 minus a half plus a third minus a quarter plus a fifth minus a sixth. Give you a couple more. Okay, and now I'm just going to divide all of these things by 2. And I'm going to stick some zeros in between. So 0 plus a half, so I've divided this term by 2, plus 0 minus a quarter, so I've divided this term by 2, plus 0 plus a sixth. This term has been divided by 2. Plus 0 minus an eighth. All right, this term is divided by 2. All I'm doing is saying if I take half of this, it should be the same as taking half of this. I'm just dividing all the terms out by 2. I've done nothing really fancy there. And now let's try to add these two things up. So log of 2 plus half log of 2 is 3/2 log 2. And what do I get? I get 1, okay, plus 0, plus a third, minus a half, okay, plus a fifth. Okay, I get 0, plus a seventh, minus a quarter, okay, and you can hopefully start to see the pattern coming, right? I get a 1, okay, a blank, my next odd term. Then for my next even term, I've doubled it, so I get an even term. Okay, next odd term, a blank, next odd term, a minus with my next even term. That's this series here, right? This is all exactly the same terms we started with in our alternating harmonic series. All I've done is I've written them in a different order. This is a rearrangement, the one we were talking about, of yeah, you can rearrange it to do anything you want. Okay, so on the one hand, we took the terms in our alternating harmonic series and we made them add up to log of 2, right, when we do it the standard way. And now all I've done is I've taken all exactly the same numbers. I've just swapped the order a little bit, but I've the same numbers. I've added them up and I've made them add up to 3/2 of log 2, different value. So this is why when Zachary asked earlier in the class, well, we have this series, and if you sort of break it up, you've clearly got two different series that converge. Is that okay? Maybe. The answer is maybe, and maybe not. Because here, I've taken things and I've broken it up in a different way, and I'm coming to a completely different conclusion about what's happening here. So let me tell you when it is safe and when it is not safe to rearrange your series. If you have a series that is absolutely convergent, then you're fine. So all your terms are positive, or you take the absolute values and you're fine. So A and B absolutely convergent. Okay, and let Bn be any rearrangement. So you started with a series. you know it converges so strongly that even if you take the absolute values of things, you still have convergence. So add up 1 over n squared, or add up minus 1 to the n over n squared. You take those terms, rearrange them any way you like, and it's fine. You haven't changed anything. Okay? So this is the conclusion. I'm not going to prove it. I'm just going to give you the result. Also converges. Okay, and has the same value. Okay, so if you have a series, you know it converges absolutely, and there's some manipulations you want to do with it, carry on. You're fine. You're safe. No problem. Now, when we did this example, the alternating harmonic series, that doesn't fit in here, because the alternating harmonic series converges conditionally and doesn't converge absolutely. So this is part 2. Okay, so let's let our series be conditionally convergent. Okay, and choose any real number that you like. Okay, then somewhere out there, there is a rearrangement of the series that actually converges to R. Okay, so here we started with a series that converged conditionally to log of 2. We found a rearrangement that converged to 3/2 log of 2. But we could have found a rearrangement that converged to -1, or that converged to 2003, or that converged to E, or whatever you like. I don't say that it's easy to write down explicitly such a rearrangement. I don't say that at all. But there is one out there. So anytime you have a series, an infinite series, if the convergence is conditional, or if you're not sure, don't start rearranging the terms, right? You will get into trouble rearranging the terms. You come up with completely different results than what you want. So it's kind of a fun example, and also a good warning that your intuition doesn't always work, right? Once you get into the infinite, we've got great intuition that says I can rearrange things. Okay, if you're playing with the partial sums, right? If you've written down a partial sum, you've only got finitely many things in there. You can add them up in any order you want. That's fine. But once you take the limit to infinity, you've got to be careful.
So what is it about adding up infinite terms that like makes our intuition, I guess, null and void? What are we missing?
Because our intuition is very finite. Our brains are very finite. It's probably the short answer to that.
But the signs changing.
The signs changing matters, yeah.
If I put all of the positive terms that you made.
Yeah, so in some sense, by rearranging things, all of a sudden, you know, by adding up a bunch of the odds and then an even, a bunch of the odds and the even, somehow you're giving maybe more weight to the odds, right, and less to the evens, or something like that. Again, I don't have a really concrete, satisfying answer, but except to say, be careful. So I'll leave you there.